Have you ever imagined that the very fabric of our universe, the vacuum of space itself, might not be as stable as it seems? Today, in this advanced physics dialogue, we'll venture into a truly unsettling concept: the idea that the quantum vacuum, the supposed empty stage on which all the drama of the cosmos plays out, might be inherently unstable. This is the theory of quantum vacuum instability, and if you've never heard of it, prepare to have your mind expanded. Let's set the stage with a simple premise. What we call vacuum isn't really empty. Even in the most pristine, empty region of space, quantum field theory tells us that what appears to be void is actually teeming with activity at an unimaginably small scale. Virtual particles pop in and out of existence due to fluctuations in the quantum fields, their fleeting presences accounting for phenomena like the Casimir effect and the very structure of the fabric of space-time itself. This quantum vacuum is often imagined as the lowest energy state of our universe, a kind of resting state. But what if this ground state isn't the true ground state? What if something deeper and far more stable exists beneath it, and our current vacuum is just a precarious local minimum? This possibility is not just a flight of theoretical fancy. It's rooted in the mathematical architecture of quantum field theory and is connected to one of the most pressing questions in modern physics: the shape of the potential energy landscape for fields like the Higgs field. The Higgs boson, famously discovered in the early 21st century, is crucial in giving particles their mass. It's tied to a field that permeates all of space-time, and its so-called vacuum expectation value specifies how it interacts. But here's the catch. The stability of the Higgs field depends on the precise values of fundamental constants. Recent theoretical and experimental work suggests that we lie dangerously close to parameters that could render this vacuum metastable, meaning it's not the ultimate resting point. It's more like a climber resting briefly in a shallow valley, unaware of a much deeper drop just a little further down the slope. Were a quantum tunneling event to occur, and this is not just theoretical, but possible, though unimaginably rare, it could push space-time into a lower energy, more stable vacuum configuration. The implications of such a vacuum decay would be catastrophic, dissolving all known particles and forces as we understand them. Now, you might be thinking, surely this isn't a real concern. Isn't the universe incredibly large and ancient? Shouldn't such an event have already happened? Well, it turns out that the answer depends on the dynamics of how this metastable vacuum behaves. The only thing dividing us from total vacuum collapse is a subtle energy barrier. This could be breached spontaneously by quantum tunneling, similar to how radioactive decay occurs when particles escape nuclear energy barriers, or it could be catalyzed by extraordinary energies, like those involved in collisions beyond anything we've experimentally achieved. Some physicists have argued that cosmic rays or high-energy phenomena in the early universe could have triggered these vacuum transitions. After all, at scales much more energetic than the Large Hadron Collider, the possibility for tunneling should have been even greater. The fact that we're still here is either a stroke of profound luck or an indication of some deeper physical principle protecting us. Could some aspect of the universe's design be inherently preventing vacuum instability? Now, this touches upon deeply philosophical questions about the nature of our cosmos. If our vacuum truly is in a metastable state, why does it appear to be so alarmingly close to the parameters for instability? This is sometimes called the Higgs instability problem, and it has tantalizing implications for theories beyond the standard model of particle physics, including supersymmetry and string theory. Perhaps there exist as yet undiscovered symmetries or laws that keep our vacuum from descending into chaos, ensuring the universe's longevity. Or perhaps our universe is merely a bubble in a multiverse sea, our little pocket metastable while surrounded by other vacuums of varying stability. One of the most fascinating aspects of this hypothesis is its potential link to cosmology. Hans-Peter Dürr and others have suggested that inflation, an extraordinarily fast expansion of the universe in its earliest moments, might reflect a transition between vacua. During inflation, space-time itself exploded outward, smoothing energy variations and setting the conditions for structure formation. Could inflation have been instability in action, a quantum leap from one vacuum to another? And if so, does this mean vacuum transitions are cyclical, driving phases of creation and destruction on grand scales of time and space? Let's pause for a moment and consider the practical implications of all this. Just as engineers factor structural integrity into the design of buildings, physicists seek to understand the stability of the universe on all levels. What if experiments designed to probe deeper into the quantum realm, advancing collider technologies far beyond the Large Hadron Collider, accidentally catalyze a vacuum decay? This concern gained media traction when the Higgs boson was discovered, but most experts agree the energies needed to tip the vacuum into a catastrophe are far greater than anything achievable artificially. Natural cosmic processes, such as gamma-ray bursts and black hole collisions, are far more likely instigators, though even these are unlikely given our continued existence. But here lies a profound paradox. The more we study the quantum vacuum, the greater our awareness of its fundamental mystery grows. Is our universe's stability a signpost of some underlying cosmic engineering? Or does it reflect an uncomfortable truth that just as stars burn out and galaxies collapse, the vacuum itself is impermanent, subject to inevitable instability? What truly astounds me is there's no definitive answer here. Ongoing investigations into quantum gravity, dark energy, and the very early universe may one day help resolve the enigma of vacuum stability. Techniques like loop quantum gravity and string theoretic frameworks are showing promise in describing space-time, not as a mere backdrop, but as a tangible dynamic entity shaped by quantum properties. Each step deepens both our understanding and the existential magnitude of the questions left unresolved. As we bring today's dialogue to a close, I pose to you this final inquiry. If we are living on borrowed time within a metastable vacuum, does this change how we view our place in the cosmos? Are we explorers on a ship navigating uncertain waters, forever balancing between the known and the unimaginable? Perhaps the ultimate gift of such theories isn't fear, but humility, an invitation to embrace this delicate, fleeting stability for the marvel that it is. Comment below. Do you think the universe has a protective design? Or are we simply surfing on cosmic happenstance? Let's explore this together in the comment section.